Stanford, yes. David isn't here.
And she will speak about massive particle production and oscillatory non-Gaussianity searches.
Okay, so let me start by thanking the organizers for this wonderful meeting. It's really been a lot of fun, and happy birthday, David, wherever you are. So I'm going to discuss a topic which I think fits in with the theme of field theory, string theory, and beyond, which is the subject of the title of non-Gaussianity searches in cosmological data. This is work that we're doing with Raphael Flauger, Mehrdad Mirbabai, and Leonardo Senatore, along with some members of the Planck collaboration. So as we heard on Monday from none other than Brezin, the interesting models are in fact non-Gaussian. So I think that's the only motivation that we need. So this is a subject that really does have an interface between these three things. So let me start by kind of reminding you briefly about the early universe observables that are getting more and more accessible through cosmological observations. And this is in the context of inflationary theory, which I think everybody knows very well. So I'll just start with the perturbations. So here's a expression for the metric, which has picked out the physical degrees of freedom in both tensor modes, gamma ij, and the scalar mode, which is often parameterized in a gauge where it arises in the metric in this zeta variable that I've written. It can be shuffled back and forth between that and perturbations of the putative inflaton field, as usual. And the basic observations have to do with the two-point function of the scalar perturbations, which is measured to be approximately scale invariant with by now a well-measured small tilt. The famous tensor to scalar ratio, which is getting probed in a serious way now by observations, and will, in the next several years, probably constrain it within the Planck field range, which is an important threshold. And then the higher statistics of the scalar perturbations, the so-called non-Gaussianities, which have, in principle, a huge amount of information in them, being non-trivial functions of three momenta, which again, on average, need to be scale invariant, but can have a lot of structure in them, as can the power spectrum. The power spectrum can have more structure in it than just these two parameters. And the data is getting to the point where one can test rather precisely very specific mechanisms for these things. So this is just meant to remind you of the basic observables. If you have any questions that you want to discuss, stop me. So when it comes to the non-Gaussianities, which will be the subject of this talk, the data analysis is basically twofold. First of all, you do just kind of a very general, not optimal, but very nice general test, which is to just take the pixels. I'm sorry this isn't coming out well, but you just take the observed pixels in position space. Okay, good, because it's really important. It's yeah. So one of the things, actually when Planck releases their data, on non-Gaussianity, they do it in two different papers. One is the constraints on primordial non-Gaussianity, which does the thing I'll focus on mostly here, template-based searches. But there's a paper on anisotropy and statistics, or isotropy and statistics, which does simple things like take the temperature map, bin it in some way, and just add up the points with a given temperature fluctuation. And over here, apparently, you can see that, it's very, very Gaussian. And, one can be quantitative about that. However, it's not the optimal test of Gaussianity, since, as we all know, as field theorists, the 3 and higher point correlation functions have a lot of information in them. They have a lot of structure in them. And with a specific enough theory, you can test the data for a template based on this detailed correlation function. So
why
yeah.
do you need a template? Can't you just have some render that's independent of any
Well, so the best you can do in that regard is something like what I started with. So that's why I mentioned. Well, it it gives you some information, but if you have a template for something like this with just a few parameters, you can do much better than. I mean, there's a finite amount of data, so you're in danger of overfitting. And if you tried to just search for arbitrary functions, you would just overfit the data, and you'd have no way of getting useful constraints. So I'm going to come back to that because there's been a lot of really interesting interplay between the sort of top-down and bottom-up effective field theory discussion of how to be as systematic as possible about this. And I'll say more about it. So it's a good thing to discuss. But it is quite clear, and it was realized, there's been a renaissance over the last 10, 15 years, understanding how to be optimal about it for a given template. And there, the signal to noise is basically characterized by the 3-point function divided by the intrinsic quantum fluctuations captured by the 2-point function. And the sensitivity, the limiting sensitivity is 1 over the square root of the number of pixels, which is basically 10 to the minus 3 for Planck, say. Okay, so, yeah.
Yeah. What is the value predicted by Einstein gravity?
Yeah, so it's basically a couple orders of magnitude below this, or maybe I should say maybe 1 order of magnitude below this, roughly. Yeah, I'll say a bit more. So there certainly is non-Gaussianity for the reason that Shiraz just said. It's just very small. And so, okay, I'd already basically said this, but there's a well-understood way to not just calculate these field theoretic correlation functions, but weight them with the data, with the right signal, with the right weighting in the data to compute overlaps between different templates and determine how many independent searches you need to do. So it's understood how to do that. And so if there's a theoretical motivation for some shape of these correlation functions, one then checks that whether or not it overlaps with previous searches or not. And if not, then it has to be done again, done in itself. Okay, so just to continue the generalities very briefly, inflation used to be just presumed Gaussian because intuitively in the slow roll case, you have this flat potential, and so the interactions of the scalar field are therefore small, and you wouldn't expect large non-Gaussianity. You do have the intrinsic ones that, again, Shiraz just mentioned. However, there's a lot of what you might consider more generic dynamics which could introduce non-Gaussianity. For example, it's well understood now that self-interactions of the field can slow it down. That's a completely different type of mechanism from slow roll inflation. And in those cases, naturally, the non-Gaussianities are, in the perturbations turn out to be larger. And the shape of them is quite different from others, such as a pre-existing large class of non-Gaussian mechanisms which involve additional light fields. So even if the inflaton is, say, a slow roll field, transverse directions can exist, and if they're light, make a difference in the perturbations. And those transverse directions have no reason to be as weakly interacting, even in a slow roll situation. And that gives a different kind of shape. It couples long and short modes in the so-called squeezed or local shape. And one of the reasons we're interested, in addition to some data-driven reasons, is that we're finding a third way that this can happen, which is interesting. And it has to do with the title that I mentioned of heavy particle production. So before I finish that, let me say that there are many shapes that have been studied. Some of them, though, are small. I mean, they just are difficult to see. And the closest one to the one I'm going to talk about is something called resonant non-Gaussianity, which comes from oscillatory terms in a potential, such as we obtain from axions, which has been studied a lot and has motivated a lot of searches. But if you're careful about it, you find that the non-Gaussianity that it can generate is parametrically subdominant to the structures in the power spectrum that it should produce over almost all frequencies. And so one of the other motivations for what I'm talking about here is, in the context of this recent history, And what we'll find is that the mechanism I'm going to talk about has a kind of oscillatory structure, but its amplitude is different, and the non-Gaussianity can be quite competitive or more with the power spectrum structure that it would produce. So when it comes to these non-Gaussianity searches, people try and be careful. It's a lot of work. So really, this is less well motivated than at the level of non-Gaussianity than what I'm going to talk about. Another case that's also somewhat similar, but just happens to be smaller in amplitude than what I'm going to discuss, it goes under the name of quasi-single field inflation, where one considers the effects of additional massive fields on the perturbations, but considers their production, their own fluctuations that result simply from the Hubble expansion. And these are suppressed by the obvious thing, e to the minus mass over Hubble. But they can be seen in some particular cases. Here, what we're going to be dealing with is repeated particle production effects that also happen for example, in axion directions in field space, for which the exponential suppression is not with respect to Hubble, but with respect to the phi dot scale, the scale of the rolling scalar field, which in inflation is several orders of magnitude higher than the Hubble scale. So let me finish this general discussion with the bottom-up point of view. So I gave kind of the top-down intuition for how non-Gaussianity arises. One can try and be systematic from the bottom up, and there's this famous effective field theory of inflationary perturbations, which organizes the well-known problem of computing inflationary perturbations in terms of the spontaneously broken time translations with a corresponding pion-like field that's related to zeta, the one I wrote, linearly in this way, plus corrections. In some sense, it's a very nice choice of gauge for computing cosmological perturbations. And by organizing it this way, you get a lot of nice theorems that were proved. For example, if you impose additional symmetries beyond what you need to just get inflation to happen, like a continuous shift symmetry, but this is more subtle, a discrete shift symmetry like we'll talk about, you get, for a continuous shift symmetry, you get just a few operators that contribute to the non-Gaussianity, and you can do a complete job of searching for those, okay? You can also prove theorems about which shapes can arise with, which shapes require, if you discover them, the presence of additional light fields, and you recover previous examples as special cases. So it's a beautiful thing. However, if you don't impose any extra symmetry, but just impose that you want to do inflation, it turns out it's not that constraining, even at the single field level. Furthermore, as we'll see in this talk, generically the data is precise enough that heavy fields cannot generally be integrated out. So you get exponentially suppressed effects, which nonetheless can be can be constrained. So it's a very useful thing, both because with extra assumptions, it limits things, but also because it tells you how far it goes and how far it doesn't go. And in fact, it doesn't fully constrain the possibilities. So I would say it's not really known how to be totally systematic about this, and instead, we test particular mechanisms that seem reasonable and interesting in their own right. Okay, so the results, of course, are that everything is consistent with Gaussianity so far, not just because of that curve, that invisible curve I showed you, but but in the cases of particular templates that have been tested carefully. For example, the ones that follow from Symmetry, these three, a number of others that have been studied, and there are some little possible hints in the case of oscillatory structures. So here's that just from the Planck non-Gaussianity paper, where they describe searches for these log-spaced oscillations that you get from sinusoidal dependence on the inflaton. And if you modulate these constant shapes with such sinusoidal oscillations, and you allow multiple frequencies, they claim some 3 sigma stuff after look elsewhere, which is not enough for a detection, but it's something that needs to be looked at more. Also, there's a little bit of numerology, which is that they certainly do look at the power spectrum. They find, although at low significance, they find certain frequencies are better fits, and you can compare those to the ones in these non-Gaussian searches. And okay, there are some coincidences, that could just be true in a Gaussian simulation, but this, again, motivates a further search or a joint analysis. And for that, one really does want to understand that when it's only motivated, fully if it's really true that the bispectrum and power spectrum can be competitive in their amplitude. So that's another reason to look further at this. Of course, things like this are usually just fluctuations, but I think this is something we really should follow up on. So we're doing that, and we learned something from the process. On the other hand, I'll be the first to admit that I have something of a gambling problem, and the house always wins. But I think that null results, null results are very interesting and informative. So we had some voting about certain things last night, and to me, it's the science is what's important. And a null result on something, you say supersymmetry or whatever your favorite idea is extremely interesting. It's in fact more interesting the more interesting the idea is. And so we go in with that attitude, and then I think everything is fine. Also, we don't need to vote. What's that?
Positive results are even better.
I don't know. We just want to know what's true. The only thing that's bad is if the experiment doesn't work or something. We just want to know what's true, and we don't need to vote. But it's incredibly fortunate and convenient in situations like this and like R and stuff, where we just don't need to vote. We can just see what is true. Well, I already told you the number of pixels is finite, 10 to the 6th. So certainly we get constraints that are not perfect. And here, I want to emphasize both. I'm glad you asked, because what I'm saying is there's a window of parameters where even though this thing is exponentially suppressed, and actually there are some parallel factors that are large in front of it that I'll mention, even though it's exponentially suppressed, there's a window where a certain mass can be bigger than this very high phi dot scale and still be constrainable. Okay, of course it doesn't follow that you can maybe it's not obvious, but this will not be enough to falsify the whole mechanism, et cetera, because this thing can be too small. However, again, it's such a rare privilege to be able to test anything cleanly that we're just going to do it. So now let me just get to the point, which is that these situations with a discrete shift symmetry are motivated by axions, in particular in string theory, where what would have been axions are typically unwound by couplings to fluxes and branes. This is called axion monodromy. And you can just take that point and follow through on the phenomenology. So one thing that also happens very clearly in particular in the string theory versions of this is that there are heavy fields around in addition to the axion. And that they have periodically varying, the mass spectrum is periodically varying. There's large sectors of the theory which have periodically varying masses. So there's some time variation in the masses, even though the masses never get lower than some scale mu that we'll talk more about. The variation could lead to non-adiabatic effects, and those non-adiabatic effects are suppressed by this exponential. And okay, so I keep saying the same thing. So these are the scales to have in mind. There's the Planck scale, there's the scale of the potential. This is all in slow roll. There's the Hubble scale. The inflaton perturbations are much lighter than that. This phi dot scale is, higher than that by a factor of the square root of the perturbation. If you're familiar with the calculation of the power spectrum in slow roll inflation, you know that it goes like h to the 4th over phi dot squared. So this is just the 4th root of that familiar 10 to the 5. And these mu's that I'm talking about can be up here. And this is really, as far as we know, this is the first time that window has been understood to be probable. So just for that reason, it's an interesting exercise. Heavy fields do affect results in in interesting but more indirect ways. For example, we already thought about the heavy moduli in string theory and what they do, and they back react. Of course, sometimes that causes the whole thing to destabilize, but when it doesn't, it just adjusts in an energetically favorable way and tends to flatten the potential out, especially at large field range, which explains the bizarre sub-integer powers of the inflaton that we get in the stringy versions of chaotic inflation. So heavy fields have been understood to make a difference, but you can't just take the data and invert it and learn that. So anyway, this is a different effect of heavy fields. So let me say a little bit more about this periodic spectrum. So there are two obvious places where that does come from the top down. One is that the branch structure of the potential that we're used to dealing with is mirrored in a branch structure of non-space filling objects in the theory in exactly the same way. So there are different sectors of heavy fields, let's call them chi, or strings, which come down each underlying period. A different sector comes down each period. And separately from that, there are these heavy moduli fields, which couple into the sinusoidal term in the potential, giving sinusoidally varying masses. So these are two very different mass formulas. In one case, the field comes down and it just keeps growing, and the other case, it's sinusoidally varying. In fact, these can induce that, and one can and should assess the radiative stability of the whole thing, which we do. Okay, so just for fun, the using of one sector to induce the other follows from a Coleman-Weinberg calculation where we can just take the usual trace log formula, sum it up over all these events, over all these periods, and get a closed form expression that gives such a contribution. It doesn't matter, we all know that there is that sinusoidal term for one reason or another, but this is kind of self-contained origin for it in this context. Okay, so the basic point is that given that the masses are varying, there's some level of non-adiabaticity which one can compute, and once these heavy chi fields are produced at some computable level, like which I've given here, the coupling to the inflaton field through the phi-dependent mass sources inflaton modes. So the computation is relatively simple. It's just to compute the production of these chi fields, and in the resulting state that has a non-zero density and definite statistics of the chi fields, the usual kind of squeeze state that you get from particle production, one can compute then the correlators of the source of phi and convolve that with the Green's function to determine the corresponding endpoint functions of the scalar perturbations. So that's the calculation. And the density, the average density that you obtain from this physics, it depends in a simple way on the phi dot, the rolling scalar field velocity at the time of production, and the slightest mass scale. And this is repeated again because of the underlying periodicity, which appears naturally for axions. So each of these produced sectors dilutes with Hubble, but the production event is kind of like a Bremsstrahlung source for phi, and then it gets repeated over and over. There's some fun subtleties, but because these templates are so precise, we need to test something clearly. We obviously have to capture the leading effects, and just to mention it in the calculation of these correlation functions, there are different terms, some of which are, so the source for phi, as I mentioned earlier, is basically this operator, chi squared dm d phi, and this is a weak perturbative calculation, and sort of the A dagger A part of this is what I gives the result I just mentioned with that density that I gave, that's phi dot to the 3/2 times the exponential. There are other terms that are coming from the other pieces of that current, which oscillate rapidly. And indeed, one can check that these terms, which are interesting otherwise because they're kind of quantum interference terms, they oscillate rapidly and don't contribute when we integrate against the Green's function. So other subtleties involve the fact that if you're looking for this kind of signal, again, because we have in mind, or you should consider, the possibility of heavy fields such as stringy moduli that could adjust during the process, everything's a function of that. The oscillation itself could drift as a result of that. So we took a look at that before the last Planck release just to see how big of a deal it was. Fortunately, it turns out it's not too big a deal in a wide range of frequencies, but it is for sufficiently high frequencies. Okay, so again, the calculation is conceptually very simple. There's a source that's produced through the particle production and convolved with the Green's function in de Sitter space, which I've given here. You get the correlators of the scalar perturbations. And so in terms of this integral, which is basically the convolution of the source with that Green's function, here is the answer for those delta phi correlators, which can be traded for the standard scalar variables zeta that I talked about and so on. Of course, the results for these sums that appear here depend on this convolution and hence on the form of the mass function. And I gave two cases: the case where there are different sectors that come down, a different one each time, and the ones that are whose masses are modulated by the sinusoidal term, and those give different answers for this. They're both interesting in different ways, and the basic reason that we find that the non-Gaussianity can be stronger here than in the previous case I mentioned, the so-called resonant non-Gaussianity case, has to do with the way that this oscillating mass can resonate with the Green's function, the oscillations in the Green's function. So in the case of the oscillating masses, the thing I called case B, you can work that out, and you find that this function h scales like some coupling times the square root of the frequency of these events in Hubble units, which ranges up to something like 300 within the range of a controlled low energy description of these oscillating terms. That is, if we keep omega less than the scale f, we consider a range of frequencies up to about 300, it turns out. Okay, so that enhancement is quite different from the case of the non-Gaussian entities that you derive simply from the interactions intrinsic to the single field inflation with the oscillatory term, for which the corresponding ratio is always less than 1 in the weak coupling regime. It's interesting. It has also a different shape. So the amplitude is big enough to make the non-Gaussianity analysis well motivated, and the shape is also somewhat different. There are these FNL parameters, which is just another way of saying the same thing. And here, well, you can kind of see here there are some large factors beyond. There's some large factors in this sort of power law stuff in this formula that also allow this to be sensitive for this exponentially suppressed n chi being, relatively small. So you get from this specific templates that can be analyzed, and you check, when they overlap and when they don't with previous searches, and that gives you a range of parameters such as this frequency to scan over. So here are some pictures of the templates in certain directions. And okay, so that's the basic story with these new shapes and their large amplitude. So let's discuss just a little bit more what Ofer was kind of getting at, which is what one can do in general. And in fact, it's not totally clear how to be completely systematic about this because the data is limited, so you don't want to overuse it. And if you take this effective field theory point of view, you can just say, well, let's see if we can cover everything that's related to that just comes from a single field. And okay, you get the effective action that they derived in terms of this delta t equals pi variable. And as you can see here, if you don't make any further assumptions, you have arbitrary functions of time and hence of pi that appear. It's not literally infinite because the number of Fourier modes that really can come into given the finite scales involved is limited. So, for example, you don't have smaller jumps in frequency than the inverse of the overall time of inflation, for example. And at the higher end, the resolution is limited by the finite time scale of recombination. So it's a finite sum that you would need to check. But still, it's a huge number of parameters. So furthermore, restricting to this purely single field thing is less and less well motivated given what we saw here, that even heavy fields can be important, can be constrainable. So, strictly speaking, those would be a multi-field version of this and would require the chi fields I had to be added in. So, given that you have to do that even if the fields are quite heavy, it seems to me very difficult to be systematic. In some sense that's good. It means that any detection is more compelling as evidence for whatever motivated it. But I think this is the situation. Of course, if you impose extra symmetries, you do get a few shapes that can be completely dealt with. Okay, so I think that's about it. Oh, I should have mentioned that I think Sunny had some interesting comments about particle production in the past involving pre-inflationary particle production that I think is a little bit different, but also interesting. In fact, the cold spot is kind of an outlier in that Gaussian curve I drew. Okay, but so here's the summary. We're trying to be systematic in theory and observations as we can with non-Gaussianity. There's oscillatory feature searches that are underway and that have some interesting structures in them that motivated looking more closely at the theories that generated this. And we found a mechanism that we really should have put our finger on previously to do with the periodic behavior of the masses of even very heavy fields. And so for all these reasons, we're following through on this. And again, it would be interesting to see if there is a better idea for how to be totally systematic given the understandable limitations of the effective field theory treatment. So let me stop there.
We do have time for questions. Yes, Martin.
I'm a little confused about the contribution of heavy fields. Is this at very late times of inflation, like close to the time of the
No, this throughout. So there's this periodic, there's this discrete shift symmetry. So there's a discrete shift symmetry. So the fields come down every period. It's a periodic effect. It's not just at the end.
But I thought it's in this slow roll scenario, sort of the phi dots are small.
Phi dot is much heavier than Hubble, right? It's small in the sense it needs to be small for slow roll inflation, but the perturbation. I mean, you know this very well, but zeta is h squared over phi dot, which is 10 to the minus 5, right? So Phi dot is a large scale in this problem. So again, if you didn't take into account the coupling of the inflaton to these heavy fields, but just considered the Hubble expansion and what that does to massive fields, you get effects, but they're suppressed by e to the minus m over h, right? And here, it's slightly different in detail, but it's again an exponential, but the denominator here is much, much higher. So, this kind of thing had been studied a lot, even though it's correspondingly harder to see. And I think this is just as generic. Was that your question?
So this corresponds to like oscillating non-Gaussian, or is there a template and all the constraints on this?
There's template. It's Planck has it. They're working on it. There are not already constraints on it. It takes a while. So, but yeah, we've checked that it doesn't overlap enough with previous searches, so it's being done separately.